Newton had another law that was just as important as the first three laws that we've already talked about, and that is his universal law of gravitation. And it can be expressed as the force of gravity is equal to a gravitational constant times the masses of the two objects in question times the distance between them. Now, when we talk about the distance between the two objects, what we're talking about is if I have an object here and an object here, and this is the centers of the two objects, that distance that we're discussing in the equation is the distance between the centers of the two objects. Now, if you've got two two relatively small objects, then you're going to definitely need to include the distance between both of them. But what happens when one of these objects is very, very massive and the other one is not? And that's what he gets into when he starts talking about the fact that if you're talking about an object like us and the Earth, the object is so massive that how far we are above the Earth doesn't really make a whole lot of difference in this calculation. And so I'm going to try to illustrate that for you. I know it seems very odd to say that any two objects in the universe actually will have a gravitational attraction to each other. The fact of the matter is that if the mass is little, then the gravitational force of that object is very, very small as well. And so in our everyday lives, the vast majority of the time, like if you've got, I think he mentioned a salt shaker and a pepper shaker, and if they're sitting on the table, you don't see them just suddenly gradually gravitate toward one another. That'd be a little weird. I think we'd kind of freak out if we saw that. They do attract one another, but the force of friction between them is so much greater that they're not actually going to move toward each other. So you have to have an object that's quite large in order to have any substantial gravitational force. Okay, so he says that if you have a massive object like the Earth, the distance away that you are from the Earth really doesn't make a whole lot of difference when we start to add it into this total distance here. So how far from the center of the Earth is far enough to matter? Well, the radius of the Earth is 6.38 times 10 to the 6th meters, which is 6,380,000 meters. So where is your estimated digit? Well, the estimated digit here is this one, and that's in the 10,000s place. So anything that you're going to add to that has to be in this area of uncertainty. So how about if I'm on the top of Mount Everest? Am I going to have a substantial difference in the pull of gravity of the Earth? Well, Mount Everest is 8,848 meters tall. And of course there is an argument between Nepal and China as to how exactly tall it is, but we're close enough. So this is in the thousands place, which is here, but here's the digit of uncertainty right here. So even if you're on top of Mount Everest, if I go to add this here, I might bump that up, I might make it round up by one more number. The difference that we're going to make is very, very, very tiny. So being on the top of Mount Everest really doesn't matter. How about if you're in a jet plane and you're at cruising altitude? Well, cruising altitude is about 35,000 feet or 12,000 meters. Okay, so at 12,000 meters, this is in the 10,000s place. The digit of uncertainty here is in the 10,000s place. So I have to be at an altitude of a jet before it even starts to make a difference as far as my distance away from the Earth. And as you can see here, this is a 1. So we're still within digit of uncertainty. And so it's even at cruising altitude of a jet, it's going to make a very, very minute difference. How about though if I get into as high as a satellite is away from the Earth? Well, at that point, height of satellites is around 35 million meters. At that point, we certainly are making a difference in the gravitational pull of the Earth. And so we have to be at that kind of a height before we have to worry about it. Now, what he says, and I don't know if you were able to kind of catch the derivation that he did. Basically what he did is he said, okay, if I put in the gravitational constant, which is 6.67 times 10 to the minus 11th, if I put in the mass of the Earth, and if I put in the radius of the Earth, if I put in those three numbers and I divide it out, I end up getting 9.8. And so I know that 9.8 times the mass of whatever object I'm talking about, that's going to be what the force of gravity is. So the force of gravity, 9.8 meters per second squared, is a really good approximation for no matter where I am on the Earth. Again, it will change slightly depending on your elevation. It does change slightly depending on exactly where you are on the Earth due to magnetic field of the Earth and all that kind of stuff, which is way beyond the scope of this course. But that's where that 9.8 comes from. If you plug in the gravitational constant, the mass of the Earth, and the radius of the Earth, and you plug those numbers out, that gives you 9.8 times whatever the mass of the object is that you're talking about. So that's where that comes from. We know that force causes acceleration, and so gravity causes an acceleration of 9.8 meters per second squared for really anything that we're going to be dealing with, especially in a first year physics course.